Last time we did some modeling, and we also looked at how to assign the strings in detail. And so once you look at, you can see the screen, is that right?
Yes, sir.
Can you see the screen with SAP 2000 model? And we also discuss in detail how we can assign these horizontal springs. For weak soil, we assign low values. And for medium soil, we went for higher values. But in this particular region, I think we have considered that it's a sandy soil. So whereas here we consider it as, yes, we consider it as sandy soil in these areas. And then after that, we consider it as a laterite soil, where because it's below the water table, we consider that the spring constant would remain the same. And then towards the bottom part, we get again soil of sandy nature due to the weathered rock. And then finally, we got the real rock with very high values of horizontal reaction values. So once you analyze this, so if you consider one particular line of piles, display deformed shape. So if you consider the deformed shape due to wind, you can see there can be small deformation, and the deformation at the top is about 0.1 millimeters. So when you model the piles and the soil, always you will get a deformation, but in the actual structure, you get the cohesion and friction of the soil as well. We are not, we are modeling only the stiffness of the soil. So because of that, the actual deformations that you get would be smaller. But here you get a small deformation at the top of the soil, top of the piles. And then we can also see the, so we'll consider one particular case next. And you can see the bending moment diagram that you get for the pile. And but if you look at the bending moment values, they are very small values for this particular case. But when you go for the combinations, you'll be able to see that if you want to see the maximum service moment on the file, we consider this particular case. And here you can see, again, you get some small moments. And you can also look at combination 2x. And when you look at 2xx, you'll find the bending moments are in the other direction. The wind is acting in the opposite direction. And because of that reason, when you go for envelopes, when you go for the envelope in x direction, here you can see you'll get bending moments on both directions. So if you want to get bending moments only in one direction, you have to just consider a combination. But if you go for the envelope, you will get a situation like this. And in addition to that, if you go to 0 and can ask it to display the moments in the shells. So we go for a combination, not the envelope, just to get some idea. So here you can see you can get the bending moments in x direction, in one direction. In this particular case, it's x direction. The variation of moments in this particular direction, that is x direction, or one direction, on shell elements. And you can see the bending moments in these connecting shell elements are very small, and these connecting shell elements are used to represent the ground slab. So these have been used to represent the ground slab. So here also I should be filling and then applying the loads, but I didn't want to spend much time on those things. Those can be done by you. So basically you can represent the ground slab at this particular level, but these slabs would be not heavily loaded, they are very lightly loaded. Whereas in the pile caps, you will get heavy moments. And if you look at the magnitude of the moment, you can see it's close to 2,300 kilonewton meters. And then you can also ask it to display M22, and you get all the moments in the other direction. So on the pile cap, you will have to provide reinforcement in both directions. And you also need to select pile cap of suitable thickness, which can resist a bending moment in excess of 2,300 kilonewton meters. So you have to carefully select the size of the pile cap. Then, so any specific questions you like to ask from the modeling we did last time? Last time I sent the models to Indunil. Indunil, are you
Yes,
there?
sir.
Yeah. Did
Yes,
you
sir.
share the models?
Yes, sir. I share.
Okay.
Yes, sir.
Okay. Right, thank you. So those are things we covered last time. So today we'll see how we can create a cellular raft and a raft, and also with the soil. So there are two situations you can deal with. One is, if you have sandy soils, then you can represent the, if you are going for a raft foundation, then you can create the ground slab, the raft, and once you create the raft can be supported on springs. The raft can be supported on springs because for sandy soils, the springs can represent the real situation. For sandy soils, springs can represent the real situation. So we'll just do we'll have a quick look at the situation that we get with sandy soils. And then we see, how we can deal with clay soils. So if you get laterite soil below the water table, you can consider it as a clay soil. Whereas if you get laterite soil with good granular materials above the water table, you can consider it as a sandy soil. Because laterite soils contain both clay and sand. So below the water table, you can generally consider it as it closely resembles the behavior of a clay soil. Whereas above the water table, it represents more of a sandy soil. So that's the way you can actually look at it. So today, what we do is we'll save it as 8. And then save it as this name. Build. Okay, now we are going to see, what is the situation that can arise with raft foundations. But, now this 20-story building. So it's generally, when you are going with raft foundations, it would be limited to about 6-7 stories, so maximum 8 to 9 stories if you get good soil conditions. So we'll consider something like a 8-story building. So what I do is I'll use this building and convert it to a 8-story building. We'll just consider 10 stories for the time being. So 8 stories maybe okay. 2, 4, 6, 8. So I'll get rid of all that. And I will get rid of this foundation as well. So now we are going to deal with raft foundation. So now we have a shorter building. Ground floor, first, second, third, fourth, fifth, sixth, seventh, and rooftop. 7th and rooftop. I'll make it 8th and rooftop. So I will replicate this at 3.6 once. So now we have an 8-story building with rooftop, and we don't have anything for the foundation. So I will create the foundation. Create the foundation. I'll get this. So I have to define the Prof foundation. So I'll add a copy of this raft 1200 and then let's say raft. So what I can do is we look at the ground level. Of a flow level. Here you can see it's 0, 7.5, 9, so 10, 12.5, 15. And here you have another shear wall, it is 1.875. So if I divide this way into 6 parts, this way also into 6 parts, then I can create or subdivide the raft into 6 segments in each direction. So what I do is I will select this and subdivide it into 6:6 ratio. And if you look at here, we have 7.5 and we like to have a node at 10. So here we have 7.5, 8.75 and 10. So that means, we are having nodes at all these locations. And we also like to have a node at 15, y is equal to 15. And here you can see at y is equal to 15 also we have nodes. So the way I have divided, all these shear walls are now connected. And we have another shear wall, short shear wall this way. And that point is taken as 18.75. And here also you can see 18.75 is here. So basically now the raft has been created so that it actually the nodes of the raft coincides with the nodes of the shear walls. So which means now the shear walls are properly connected to the raft. And we can also have a look at 3D diagram. And if you look at here, it's not very clear. So what I can do is go for 3D. I'll select all these and ask it to show only the show. I'll select here and show selection only. And then I can have a look at 3D. And then you can have a look at whether you get proper connectivity. So here you can see all these joints are connected. All these places are also connected. So basically you will get proper connectivity between these nodes and the raft foundation. And here another thing you can observe is this raft is actually at the very edge of the raft. You get columns. So one of the things we can do is extend the raft little more so that these columns can be comfortably supported. So when you are doing the actual raft, you will have some extra length. So here you can see the distance between these 2 points is 23 meters, 24 meters. Here you can see the dimension here, and here you can see it's 23 meters. Now this one is 24 meters. So what I do consider is that the raft will be extended by another 1 meter. So I'll say I'll ask it to replicate in y direction 1. So now the raft is made bigger. -1 direction that can also accept this, replicate by -1. I can replicate this. Right, okay. Now you can see there's some projection beyond the boundary of the raft. And if it is sandy soils, we have to find we can actually represent the presence of soil by using by using a set of springs. So to find the spring constant in order T-type foundations, we said that a simplified method of finding the vertical spring constant K value in kilonewtons per meter cubed is to use the formula that K is equal to factor of safety multiplied by the allowable bearing capacity multiplied by 40. So we can make use of the equation. The vertical subgrade reaction is given by factor of safety multiplied by bearing capacity multiplied by 40. These are all in your notes. But to represent this raft with springs, we have to actually multiply this by the area represented by each spring. The area represented by each spring is, here you can see the distance between 2 points is, here you can see the coordinate. Here you can see 3.75. Now you can see it's 5. So basically it is 1.25 meters this way. And here you will see that the y coordinate is 25, 24, 23, 22 and so on. So it's 1 meter in that direction. And if you are having reasonably dense sand, where we can go for a bearing capacity of around 150 kilonewtons per meter squared. And let's assume that we are having fairly dense sandy soil where we are able to go up to about 150 kilonewtons per meter squared, and then the value of K value will be equal to if you use a factor of safety of 2, and some engineers use a factor of safety of 3. So we'll assume that we are using a factor of safety of 2. Bearing capacity is 150 multiplied by 40. So you get a spring constant of 2 into 150 into 40 of 12,000 kilonewtons per meter cubed. And when you multiply this 12,000 kilonewtons per meter cubed by the area represented by each spring, which is 1 meter by 1.25 meters. So you'll find that you have to substitute a spring constant K is value of 15,000 kilonewtons per meter. So you have to multiply it by, you have to substitute the spring constant as 15,000 kilonewtons per meter deformation. So you need a load of 1,500 tons or 15,000 kilonewtons to compress the soil by 1 meter when it is behaving in the elastic region or low loads, because we have maintained the factor of safety low. But we are not talking about the consolidation settlement, but in sandy soil you don't have to worry about a consolidation settlement, because whatever the settlements will take place while the building is constructed, when you keep on adding loads, the deformations will take place, and whatever the settlement that is anticipated will occur immediately. So there's no long-term settlement. And so we can allocate a spring constant value of, so all these points we can assign joint springs in global direction having a spring constant of 15,000 at each location. And sometimes you might say that these corner ones will have less area, but what actually it's a small mistake. What is that line? There's an additional line that I have applied. So to get rid of that particular line, assign joint restraints none. Assign joint springs right. So now we have the whole building on springs, and because the whole building is on springs, we have to first, before we do the analysis, we'll have to fix one of these points. So we'll assign joint restraints in X and Y direction, but not in the Z direction. We should keep the Z direction free to move because we have already assigned springs to support the building. And then when it comes to this point, I can say I can allow movement. I don't want to restrain in the Z direction, but if I do not provide some support here, then the structure might not be properly held. So what I do is I will consider that the structure can move this way, but cannot move this way. That means in X direction it cannot move, X direction it cannot move, but in the Y direction it can move. And I select the support, Sign, joint, straight, and all in x direction. So now the structure cannot move because we have restrained its movement, and so now I can restore the full structure as well, since show over, and I can ask it to analyze. So the analysis is complete. So there's some kind of instability in the model, as you can see here. Some type of instability is there in the model. So what you can do is, it would be due to the support conditions. So what I do is I'll go to this point. I will say that, sign, joint, restraint, and here I'll say that, it can move in x direction, but it cannot move in y direction. And now we'll analyze it and see whether the problem still exists. Now I have held it in 3 positions. At this place, it's both x and y directions. Here I'm holding it only in x direction. Here I'm holding it only in y direction. And still the problem is there because some kind of instability is there in this model. So what we do is, we make it sign, can't assign it until sign, restraint, I improved on the restraints. Still the problem is there. So you have to check it for inadequate support condition. One or more. So what we do is, we'll just see what's going on by looking at the deformed shape model. And there you are. The problem is with view, two, okay, mode 1, mode 2, mode 1. There's some problem with the connectivity of the structure. So we'll look at it. Z0. this is I'll just get rid of this. So replicate at minus 1.25 once. Sine joint sine joint joint restraints and here again we have to see replicate okay. Now this location it's springs restraint is U1 U2. I will assign joint restraints no restraint. Now I'll hold this in position in x direction and allow it to expand in y direction. So I should be able to assign joint restraints. I can allow it to move in. I will not allow it to move in x direction, but I will allow it to move in y direction. So that means it can move in y direction, but not in x direction. And then at the bottom corner, I will make sure it does not move in any of the directions. Assign joint restraints. Still, I am allowing it to move in z direction. Now, I think the problem should be okay. We'll analyze it and see. Now you can see it's okay. The values are okay. Model is stable because earlier there was a connectivity problem. That's why we did not get the proper answer. And also here you can see this is an 8-story building with rooftop, and the natural period of vibration is about 0.6 9 seconds. So it may be a reasonable value, but you can always check the mass, how the mass is allocated, and see whether you need a further refinement for the natural period of vibration of the structure. And I explain how to do that by looking at the mass and finding whether you have allocated the mass properly. And then we'll see to show the undeformed shape, and also we'll go to the ground level. And so we should be able to display the force moments in the shell structure, that is the foundation, the rough foundation. And here you can see these are the lines where the columns are located, and so there you get heavy sagging moments. These are the lines where the columns are located, whereas this is the middle part. But again, here you can see a lower stress because we have many elements in this area, as you can see here. So this is the area where you get a lot of shear walls, and that's the area you have fair distribution of forces. So here you can see the sagging moment does not rise as in these areas. So this purple color is one of the highest moments. So you can see the purple color high moment appearing in between columns, whereas the moments and forces in the projection area will remain low. But still we need some projection, otherwise, the columns cannot be cast at on the correct location. The outer columns cannot be cast at the correct location. So we like to have the rough foundation projecting slight distance beyond the column line. So here we have got 1 meter and 1.25 meters in y direction 1 meter, x direction 1.25 meters. So we have projection in the building, and you can also see the bending moment values. But the important thing here is, you have to look at these moments, and in addition to the bending moment, you have to look at M12 value. And when you look at M12, you get some values like even slightly higher values like 105, and some places it's very low, 11 and so on. So when you are designing, so when you are designing, now if you look at a place like this, that is having highest sagging moment, highest hogging moment, because in this area the soil pressure is acting upwards, so it's one of the highest hogging areas. And if you look at that area, sometimes you get some moments like 70s and so on. So when you are designing, what you do is, you will design for the addition of the bending moment and the torsional moment. So when you are designing, you will not design only for the bending moment. You will look at the torsional moments and add the torsional moments to the bending moment. So I have explained this in great detail, but when we looked at, you know, how to find where to provide the reinforcement when you use finite element method, because you are getting a bending moment and a torsional moment, and how to interpret it. And if the torsional moments are relatively smaller than the actual bending moment, then you can simply add it. Simply add the torsional moment to the bending moment. But if the torsional moments are significant, or can be even higher than the bending moments, then there's a chance that, you know, not only in one phase, but on both phases, you might need to provide reinforcement if the torsional moments are high. So when you look at this particular problem, you can see the torsional moments are low values. So when you are designing, you will simply add the bending moment here and the bending moment there. So you guys can see the bending moments are in the range of 529 and 520 and so on. And this is one of the column lines. This is another column line. So in between, you know, you have to get, you are getting some values like, so in this area, you are getting some values like 8400 and so on. So when you are designing, you will design for 522 plus this torsional moment, which can be about 80 to 90 kilonewton meters. So what you do is, you know, you will add the torsional moment and the bending moment, and then do the then find the reinforcement requirement. So in addition to that, you may be able to get the shear force. So you can see the shear force values, and that is due to the bending moment acting in this direction. That is in this direction. So you can see, you can get an idea about the shear forces that are acting as well. So because when you take a shell element, it gives two moments at the edges, and then you get a vertical, the shear force, and also you get in-plane loads that we call axial loads. But we are not very interested in these axial forces because they are small, and the reinforcement that we provide will be able to easily resist those axial forces. So there, in the plane of the shell, we get the axial forces F11 and F22. In addition to that, we get a torsional moment and two bending moments. So when you are finding the reinforcement, you will add the bending moment and the torsional moment and find the reinforcement. And when the torsional moment is significantly less than the bending moment, you can just add them. Otherwise, you know, you have to consider the sign and add it carefully, as we have done in the examples that we discussed in great detail, covering all the possible aspects or all the possible scenarios. So basically, any question from this? The modeling of a rough foundation when you have sandy soil, where the soil can be easily represented by using a spring constant. Any questions on this? So if you don't have any questions, we'll take a break. And after the break, we'll see, you know, what will happen when you have clay soils and some loose pockets of clay soil and so on. so that it may be useful to have the soil also modeled to a certain extent, so that we'll be able to get a reasonable idea about the forces. But in addition to all this, I also like to show you, display joints under the same loading condition. We'll ask it to display the forces, and if you look at the forces, you can see the forces are in the range of 220, 213, 211, 207, and generally we look at, if you look at the forces under the service combination, not the ultimate combination, and here you can see the forces are in the range of 160, 150, and so on. So if the force is in the range of 160 divided by 1 divided by 1.25, because that's the area represented by each spring, 1.25 meter by 1 meter, you get a stress of around 128 kilonewtons per meter square. The soil will have a stress of about 120 kilonewtons per meter square, 128. And so we consider that the soil has a bearing capacity of 150, and the actual stress is in the range of 128, 130, and so on. So basically, the structure will be safe because we did not consider the weight of the raft. We did not consider the weight of the raft. So to the reactions, we'll have to add, or have we considered the weight of the raft? Yes, the weight of the raft also has been considered, because we use normal concrete, having the raft was defined by using normal concrete. So actually weight of the raft is also added. So basically what you see is, we have a bearing capacity of about 150, and with the raft, the stress on the sandy soils below would be in the range of 130 to 135 kilonewtons per meter square. So which means, you may be able to, if you wish, you can add another 1 or 2 floors to this particular building. And another thing you can see is, what will happen if you increase the thickness of the raft. And here you can see these values: 162, 164, 155, and so on. And so if you increase the thickness of the raft, define section properties, raft, modify it, and we'll make it 1500. We can run the analysis and see what happens to these reactions. So it's all done, and here you can see display still very similar values, but slightly higher, because now the weight of the raft is higher, and so the values are in the range of 164, 165, 165 divided by 1.125 equals, so 146 kilo newtons per meter squared stress is there, and the allowable capacity is about 150. So this will be okay, but there's no point in using thicker raft unnecessarily, and you'd better always look at the bending moments that are acting and then make a decision. So if you look at the bending moment value, they are in the range of 400, 500 and so on. So if the bending moment with the torsional effect goes up to about 600, bending alone is about 500, and if it goes up to about 600 m over bd squared, 600 into 1000 divided by 1000 divided by effective depth of 1400 squared. So you get a bending moment of 600 kilonewton meters divided by 1000 divided by m over bd squared. D is about 1400 squared. So the MOBD squared value is very low. So basically 1.5 meter raft is not necessary, except at these places where the bending moment can go up to about 900. Again, you don't need such a big thick raft. So by looking at the bending moments and the by looking at the bearing capacity and the bending moments, you can come to a conclusion whether the selected thickness is too much or not. If MOBD squared value is low, then you are having a situation where the thickness of the raft is too high, and you can actually reduce the thickness of the raft. And when you reduce the thickness of the raft, you might run into some problems with shear. And if you have any problem with shear locally, then in that region, you can provide vertical links within the raft, and these vertical links can actually help play a dual role. During the construction, these vertical links can be used to support the top mat of reinforcement in the raft. So having some shear reinforcement at local pockets is not a major problem, and you can actually have a thickness selected based on the bending moments. And when it comes to shear, it's possible to use vertical reinforcement to carry shear at local failure places, whereas in other places the concrete alone will be able to carry the shear. So this is how you can deal with it.